All right, 6-5, day 2. More on good old complex numbers in their wonderful trig form. All we really did the first day is how to convert them from standard back to, standard in trig form. A couple operations, basically multiply, divide, and to do an exponent with a complex number, right? You'll actually see if the complex number is in trig form, it actually tends to be a little bit easier to do, okay? These give you the rules that basically drive everything. If you're multiplying, you multiply the r values, but you just add the angles. If you're dividing, the exact opposite follows. Divide the values for r, subtract the angles, okay? So basically, I'm going to do just one of each, because I think you'll see that it's a pretty straightforward process. And a lot of times that's one of the advantages of trig form is the operations can be a little bit easier if that's the form you're in. Now, if we're going to do this, we need a couple of complex numbers. Let's do 2 cosine of 2 pi over 3 plus I sine 2 pi over 3. And complex number 2 will be r is 8 cosine of, let's see here, 11 pi over 6 plus I sine and I fit it all in. Nice. Couldn't finish it with a parenthesis. Actually, I'll slide over a bit and then I'll get it. Okay. So you're going to see it's a little more tedious when you're in radians. Okay. But I'll show you one of each, one in degrees and then one in radians. Remember, what we are finding here is Z1 times Z2. All right. So R is 2 for the first and 8 for the second, so I multiply those and I get 16. The angles I add, so I've got 2 pi over 3 plus 11 pi over 6. And the only difference for the imaginary component is it goes with sine. All right, so at this point, the big issue is what's 2 pi over 3 plus 11 pi over 6? Well, we should probably figure that out. Nothing too terrible here, but I do want to make note, and you guys have seen this before, that with the whole fraction element with radians, they're a bit of a pain. The next one will be in degrees, and you'll see that it's nicer with degrees. Let's see here. Need a common denominator. 4 pi over 6 that is going to be 15 pi over 6. I'm just kind of doing this work off to the side. 5 pi over 2. Okay. However, that's beyond 2 pi, and I would prefer that the angle that I give be within 0 to 2 pi, so I can take away 2 pi, and there we go. Okay, that's kind of a worst case scenario for what it took to find the angle. I gave you two angles here in radians that were not that nice to work with and gave you an answer that wasn't that nice. Most of the problems you'll have in your homework, there's not that much going on to get the angle. And again, you'll see that in the next example. All right, so we have 16 cosine of pi over 2 plus I sine of pi over 2. Now, I'm going to, this doesn't say how far to take it, I mean as far as what form you give your answer. If it said that you could give your answer in trig form, we've got it. We have the new value for r, and we have the new value for theta. I'm going to take it a step further and put it back into standard form, which really isn't that big of a thing to do. You know, what's cosine of pi over 2? Well, that's 0. What's sine of pi over 2? That's 1. And then basically I distribute the 16. There is no real component anymore. And all that's left is the imaginary component, which is 16i. Okay? So strictly an imaginary number, just 16i. All right, so let's divide. Okay, two different numbers here. I'm going to take it easy on you with the angles. Right, they're both in degrees. But we're going to do z1 divided by z2. So remember now for the angle, this is the case that I was talking about. All we need to do is 300 minus 75 to get 225. Little nicer case than dealing with those fractions. So now if I simplified the 24 over 8 to 3, I'd have my answer in trig form. 3 cosine 225 plus I sine 225. I'd go to a calculator or the unit circle, if it's on there. In this case is 225 degrees, so I'd see the cosine value is negative square root 2 over 2. And the sine value is also negative square root 2 over 2. Now at this point it really just becomes distributing the 3, and we get negative 3 square root 2 over 2. That cannot be simplified in any way. That's the real component. And then let's just switch this to subtraction. Minus 3 square root 2 over 2i, and there would be your answer in standard form. All right, last topic on complex numbers in trig form. De Moivre's theorem, which is really an extension of multiplying. Basically says this: you need to have a number in a complex number in trig form, which we have seen many times throughout 6.5. If you really, really think about this, it's the same as the multiplication rule that we saw. If you raise that number to the nth power, r you'll raise to the n, but cosine with the angle you will multiply by n. And there you go. Okay? So, let's find z to the 12th. And you're probably like, well, of what? Let's say z is, and I'm going to be not nice to you here, and I'm going to give it to you in standard form. Okay? So the very first thing you're going to have to do here is get this thing switched over. Most homework problems will not do this. I just want to make you practice switching the complex number into trig form. So we got to find r and theta. As always, I start with r. It's easier to find. Looks to be the square root of 4 or just 2. Okay? Theta, again, you've got all kinds of options at this point. I'm just going to go off of these numbers right here. And I'm going to use tangent. And if I were to do that, it's going to be negative square root 3 over 1, or just negative square root 3. And if that were the case, then theta is 2 pi over 3. Remember, if you were to plot this complex number, that the imaginary is like the y and the real is like the x. So when I'm setting this up with those two numbers, I basically did the equivalent of like y over x, which is why I did inverse tangent. All right. So we have what we need now. This would have been the nicer number to have given you and said, all right, z is 2 cosine of 2 pi over 3 plus I sine of 2 pi over 3, and from that, remember, we are looking for z to the 12th power. Well, r needs to be then raised to the 12th, and the angles in here need to be multiplied by 12. So we will have 12 times 2 pi over 3 plus I Two to the 12th power is 4,096. As we simplify the angle here, you basically have 24 pi over 8, which would just be 8 pi, plus I sine 8 pi. And at this point, you can think of 8 pi as basically 4 trips around the unit circle. So just think of the location of where you're at. You're basically at 0. If you were to go subtract 2 pi 4 times, you'd get right back to 0. So the cosine at 0 is 1, and sine is 0. So the imaginary component is gone because it's just I times 0, and we distribute the 4,096 basically times 1, and we actually see our answer is a real number. It is 4,096.